Okay, so everyone remember to take the reading quiz. Should be fairly straightforward. And there'll be some other reading going up very soon, and an additional homework. You'll notice that there's going to be 2 more homework assignments. What was I going to say? Oh yeah, sorry, I lost a train of thought. I was trying to read. My brain can only do one thing at a time. I was trying to read and talk at the same time. So there'll be a couple more homework assignments. You'll notice that, they're going to, this homework that's due on Monday should be significantly easier. The diffusion one, the one on phase transformations, you notice we didn't do a whole lot quantitatively with it. So that one will be it will be even easier. And the last ones will be just more of an exercise, in going through and just helping you put ideas straight for the exam. I want to remind everyone as well that for those of you who were unhappy with your midterm grade, there's still 2 opportunities. If you want to do a replacement paper, contact me and we can work together. I'm not putting, there's not like a rubric or instructions that are going up on Carmen because I expect each one to be different. The paper is going to be nominally about, a phase transformation that's important in or materials processing that's important in the general area that you're going. But obviously you can imagine that what's important to a welding engineer looking at doing titanium or solid state joining in nickel superalloys is going to be quite different than a material science folk who's going into BME and is looking at transformations in hydrogels, right? So then, so what the paper is really going to be a sort of a collaborative effort, right? We'll have a meeting and discuss some ideas. There's a couple students who are already taking me up on that, and we sort of had a talk and then, decide, I suggested 1 or 2 things based on their background and interest. And so that's how I want it to be. I'm also not putting that up on Carmen because I want it to make sure that it's available to people who are here and paying attention, right? So there are, some students who are not coming to labs, or as far as I could tell, participating very much and did not do well in the midterm. And I'm, kind of maybe it's a mean streak in me, but I'm less interested in helping them out than the people who are here and paying attention. It's a replacement, right? So shoot me up by either email or Carmen. They both messages come right to my inbox. And so it's and we'll just set up a quick Zoom time, or we can catch up at office hours. But yeah, it's a direct midterm replacement. The other option for, your midterm grade is the final is cumulative, right? So I am happy to replace your midterm exam with your final exam grade if you do better. although not vice versa, right? Right, you can't, your midterm grade cannot replace your final grade. Right. So now that we've got that out of the way, yes, yeah. Thanks, Nick, for calling me out on that. The homework grades will be posted. It's just a matter of getting that in there. Yes, the final exam will be a take-home like the midterm, although it will not be nearly as ball-busting. I've learned my lesson there. But it will be the same style, just not as quite as impossible. It will be a lot more, we'll say, qualitative, right? Describing what's going to happen rather than calculation. Right. I am also going to make sure everyone has a practice exam to look at, right? So basically over Thanksgiving break, I'm going to be writing two exams simultaneously, right? And then, so they're essentially the same. We'll flip a coin live on the air, so to speak, so that there's no no cheating. And whichever one you guys pick randomly will be the one that becomes the take home, and the other one will be the real exam. I'll just post them both up on Carmen and set the available date for the practice one to be whenever, whatever that Monday is. Right. I want to be as fair as possible and as helpful to you guys as possible. The mastery questions, everyone's just getting, no, you can't see both exams before you flip the coin. The mastery questions, everyone's just going to get full credit for. I couldn't make it work in Carmen. I don't want to stress anyone out. When I wrote the, when the syllabus and everything was drafted, I expected us to be back on campus by now. And since we're not, it's really thrown a wrench into a whole lot of stuff. Not just for this class, but also for, I think, every other aspect of my job. I've never put in more hours in any semester that I've been here and feel that I'm so far behind. So
I think it's getting worse.
I think it is. It's just so essentially the mastery questions are sort of at a wash. I stacking up extra stuff for you guys is just not fair right now. I thought I made an announcement about that. If I didn't, I'm really sorry. Okay. Yeah, the meme was I think how we're all feeling right now. So okay, let's so where did we leave off? So we were talking about growth of precipitates, and we basically said there's a huge analogy with the nucleation that there is a term that is your supersaturation term and your diffusion term, and they both have opposite dependence on temperature. And so that there's going to be some optimal undercooling for growth. And that optimal undercooling tends to happen at a higher temperature than that for nucleation. So the growth, so this sets up, I think, one of the basic universal truths in materials processing, that you can either be in a nucleation limited regime where growth tends to be fairly easy, right? If we're at lower undercoolings, growth is much easier than nucleation. So we only get maybe 1 or 2 nuclei, and the particles just grow really large. On the other hand, we could be in a regime where nucleation is easy, but growth is slow. And then we get a large number of very small nuclei. Most of the time, in terms of metallurgy, that's what we want. We're interested in strengthening phases as metallurgists. However, if you're trying to do, say, synthesis in the solid state, if you're a ceramicist, then you might not want that. You might want very large particles growing. So it all depends on what you're trying to achieve and where you are, where you want to be in the temperature. Okay, so we said that the important bits here is that for a planar interface, we get parabolic growth, right? Meaning that the size of the particle scales with the square root of time, right? And so if we think of what the square root equation looks like, right? It starts out steep and then not really saturates, but it increases with lower and lower and lower slope as you go on. So our growth rate decreases with time. For the lengthening of plates and needles, we have to consider the Gibbs-Thomson effect at the tip, which will tend to actually lower our supersaturation, but then we have 3D diffusion, right? We can diffuse in from all directions at this tip, and we end up with linear growth, that our growth rate is going to be constant with time. So therefore, needles will tend to lengthen very quickly, right? And because we're not expanding out, if this is a coherent interface, this is not expanding out very quickly. Essentially, that means that a spherical particle or a cuboidal particle that's growing by parabolic growth, we're going to increase by a factor of over 100 seconds. We're going to only increase by a factor of 10, right? So our interface will move over 10 units, right? Meaning that we go from, say, 1 unit to 20 units in diameter, because this interface is going and this interface is going, right? So we have a diameter of 20. If I have a precipitate, a particle like this, I'm going to have linear growth, right? Meaning that my interface is going to grow by a factor of 100 this way and 100 this way, or my length is going to go up by something that's proportional to 200, right? So whenever it's possible, we see plate-like morphologies that come up all the time, and that's because of this feature. Okay. The growth of semi-coherent or coherent interfaces, I said before that if I have a coherent interface, right, if I have a cuboidal particle and these are all coherent or semi-coherent interfaces, that this growth is going to be slow, right? We've essentially learned when we talked about solidification, right? We talked about ledge mechanisms and spiral growth mechanisms when we have a high energy, a low energy interface, right? We have a very similar thing here. The free volume associated with the coherent interface is very small, right? The growth rate is very slow. Because anytime I come and put if I put another cube up here, I'm adding a very large energy penalty, right? I have to disrupt this perfect interface in a significant way. So that means these plates are going to thicken basically by ledge growth, right? And this region here, this is coherent. This little step then is incoherent, right? Because this edge is incoherent, it actually has, it can move quickly. So our U velocity here is much, much faster than our overall growth thickening velocity, right? So we can add things to this edge very easily. Same thing as in solidification, but moving this interface this way is slow because it's just going to be one ledge passing at a time, okay? Getting quantitative with this is much more difficult in the solid state than it is in solidification because we have to take into account the geometry of diffusion, okay? So I'm not going to go through all of the details of the derivation because it means solving the diffusion equation for different configurations, and it's different for a cuboidal particle than a planar semi-coherent interface than for, say, a spherical, like if it was a needle. But the key idea is that the growth of this step is going to be proportional to 1 over this step height, right? Which makes sense, right? The bigger this step, the slower it's going to grow, right? It's also going to be proportional to the diffusivity and the undercooling, right? So intuitively, this form makes sense. I can look at all the terms here and explain and understand where they come from. The outward growth of this interface is then going to be proportional to the distance between these ledges. Basically, it's telling me that my growth rate depends completely on my supply of these ledges. If these ledges are very far apart, there's no way I can grow this way quickly, right? So again, the end result is a physical picture that makes intuitive sense. Getting from this schematic to this equation is a lot of effort and not worth it for what we need to do in this class. Okay, so we have possible mechanisms to supply these ledges, right? We can do spiral growth, right? Remember spiral growth, we had a screw dislocation coming out of the surface and we just built up like a parking ramp, right? We have repeated surface nucleation, which we already said is very hard. Nucleation at precipitate edges or nucleation at intersections or interfaces with other precipitates, right? Okay. Spiral growth is the only one that can supply ledges with a constant width, lambda, a constant wavelength. Right? And if our growth is limited by the nucleation rate of these ledges, every other mechanism is going to be much, much slower than spiral growth. So spiral growth is the dominant mechanism for the growth of coherent or semi-coherent interfaces, which means we need a dislocation, right? We need the defect in order for our precipitate to grow. That's like a very material science statement, right? Right? Everything's controlled by defects, right? We need an imperfect crystal in order for that crystal to grow. And this is backed up by experimental observation, right? So this is a plate in a TEM experiment. Gravity does normally not play any role in the solid state transformation, right? The density difference is just too large, right? Gravity is a pretty weak force, right? So whereas in solidification, yes, gravity is important. In the solid state, not at all. All right. So this is a TEM experiment. And it's, I forget exactly what it is, but I think it's a silver alloy, if I remember correctly, the experiment. But this is the thickness of a precipitate in angstroms, right? Obviously, in the TEM, it's a thin foil, so you can only, your foil is only a couple nanometers thick, so you can only have precipitates that are quite small. But what they do is track the thickness of an individual precipitate with time. And essentially what you see is hold periods where the precipitate doesn't get thicker. And then all of a sudden, it does get thicker over a period of time, right? And this is the waiting time for another ledge to nucleate. So a ledge passes, we get thicker, and then we wait and wait and wait, and we have to, there's the time dependence of waiting for the next nucleation event, right? So essentially we see ledge growth in solid state in action here. Okay. So then the last topic in diffusional phase transformations that we want to talk about is the JMAC equation or Avrami, right? And I don't think in the field of phase transformations, there's a more useful analytical framework or one that has been more abused, right? As you'll see, the beauty of this theory is that it's so simple and interpretable, which means people tend to apply it to everything, even when it's not warranted, or even when it violates all of the assumptions that are made. People still apply JMAC theory, myself included, right? We published a paper on dynamic recrystallization, and we looked at some simulations, and we basically just said that this is completely the wrong way to analyze this virtual experiment, but it's the way that all of the experimentalists analyze their real experiments. So we're going to follow suit. And that's because there really sometimes isn't another way to look at things except the wrong way. It seems odd to say that as a scientist, but there's a lot of physical insight that comes from this framework. Okay, so let's start from something that should be familiar to you, which is TTT diagrams, or time temperature transformation. And what this gives is, at various temperatures, it gives you the information of how long the transformation takes to occur to completeness, right? So I know if I hold for this amount of time, my transformation is going to be 1% complete. And if I keep holding it by this time, it will be complete. And so the time to the 1% line, essentially on this axis, tells you how long it takes before you have an observable transformation start. The width between the two curves, the distance between the two curves, tells you how long it takes for the transformation to complete. Okay. Well, why is this important? Well, often we have like many transformations that can occur, right? When we talk about steel, we talked about different ferrite, pearlite reactions, Widmanstätten, bainite, different aspects that can occur. And if what I know from here is if I cool quickly, I can miss the nose of this curve, right? And I can get down to a regime where whatever this transformation isn't going to happen anymore. And I could be in a more favorable range for some other transformation that I want to occur. Okay. But what we want to get across from throwing this picture up now here is that the transformation tend to follow these sigmoidal curves. If I look at the fraction complete between 0 and 1, I get a sigmoidal structure, sigmoidal shape like this to my fraction. And obviously this is, of course, for transformations that go to completion, right? And we're interested in what is the rate at which this happens. We want to be able to analyze this rate in some way, shape, or form. I want to know how easy it is. If I experiment, I can do this experimentally at some different temperatures. And I want a framework that helps me know, so basically, where is this going to start and where is it going to end, and how fast is my transformation going to go in between? Okay. So we have a couple different ways. Before I said all this depends on the transformation going to completion, right? And so that means we have what we call it essentially a cellular transformation, right? I have alpha going to beta, say, so I have nuclei of beta, and these nuclei are then going to grow until they impinge, and all of the alpha is consumed, right? So when all of the one phase essentially is consumed, we call that a cellular transformation. We could have a case up here where we have supersaturated alpha going to alpha plus beta, say, right? And then we have nuclei, and these nuclei are going to grow, and we could have two cases. We could have continuous nucleation through the whole transformation, right? Meaning we have a constant nucleation rate, right? These are kind of idealized limiting cases throughout the whole transformation, but then eventually the concentration of B in our alpha gets low enough and our transformation stops. We don't go to 100% to completion. We can also have the other limiting nucleation case where instead of nucleating continuously throughout the transformation, we can say all of the sites nucleate at once and they all grow, right? So in this case, we're going to end up with essentially a uniform, all the beta particles are going to be the same size. Up here, we're going to have a continuous distribution. We're going to have some particles that nucleated at the beginning are going to be the largest. And we're going to have a distribution of sizes down to the ones that just nucleated right before the transformation ended. Right? So what does JMAC, which case does JMAC apply to? Well, it's kind of not any of these, right? What we do assume is that we have continuous homogeneous nucleation, but that it also goes to completion, right? So it's not exactly one of these idealized cases, and we'll go through the assumptions in a minute. Okay, so what is JMAC? And I typed it wrong here. JCAM. So the JMAC equation is a simple model of how solids transform from one phase to the other at constant temperatures. Okay, it's a homogenized equation, or a mean field or average volume equation, because it doesn't tell you anything about what's happening locally in your microstructure. It tells you about the volume fraction in your microstructure as a function of time. Okay, it can be used for a wide range of systems: crystallization or phase transformation, other changes of phase in material, even things like spin transitions in quantum materials, also in chemical reaction rates. Sometimes it's used in ecological systems. Okay, so the equation was first derived by Kolmogorov in Russia in 1937, and he got his work got zero notice, and no one paid any attention to it. And then a couple years later, a guy at Temple University named Melvin Avrami, who is a chemical engineer, he published a series of articles in 1939 to 1941 where he laid out the exact same theory, and that everyone noticed. Right? So for many, many years, this theory was called the Avrami equation, right? Maybe in the last 20 years or so, people have really looked and was like, yeah, we're not giving this guy Kolmogorov the right credit. They also basically said we should give Johnson and Mayle, who wrote another seminal paper, credit. So now we call this the JMAC theory. However, chemical engineers resist it, and it's still called the Avrami equation in the chemical engineering literature. The equation is really easy to use and interpret, but it's oversimplified, right? It's at best a rough approximation of reality. Okay, so what are the assumptions in JMAC theory? Okay, so first, we assume we have a transformation alpha to beta. Okay, and that the nucleation occurs randomly and homogeneously over the entire untransformed portion of the material with time. Okay, so that means the nucleation rate has to be proportional to the amount of alpha we have left, right? Or we can think about is the overall nucleation rate. The nucleation rate per volume or per mole obviously stays constant. But if we have a chunk of 1 mole of total material, the number of nuclei as a function of time is going to decrease, because the fraction of alpha that we have left is also going to decrease. Okay, the growth rate does not depend on the extent of the transformation. We just spent a lot of time talking about why that is possibly wrong, right? When the fusion fields overlap each other, we have less undercooling. I mean, we have less supersaturation, so the growth rate is going to slow down. Well, simplifying assumption, we're going to say the growth rate does not depend on the extent of the transformation. Growth occurs the same in all directions. So we have perfectly isotropic particles. Well, we just spent a lot of time talking about how that's clearly not true because semi-coherent and coherent interfaces grow at a much, much slower rate than incoherent interfaces. So particles continue to grow until they impinge on each other, and the transformation is going to continue until all the alpha is consumed. Okay, so basically what that means is we have a nucleation rate per unit volume that stays constant. The particles then grow at a constant rate into spherical particles, and they only stop growing when they impinge, when they hit each other. Right? So those are the assumptions. The derivation is actually really straightforward. So if the cells grow as spheres at constant volume, let's think about if we nucleate a sphere at time 0, the volume of it, of this sphere, is just 4/3 pi r cubed. Right? The radius is given by the velocity of this interface times the time. How far has this interface moved over? So that means the velocity as a function of time is just 4/3 pi v cubed t cubed. Right? Okay, so what about a particle that didn't nucleate at time 0, but nucleated later at some time t equals tau? Okay. So if we're at 2 seconds here, if it say we nucleated at 2 seconds in, and we're currently at 5 seconds, right? We just have the volume of this particle is 4/3 pi the velocity cubed times 5 seconds minus 2 seconds. This grew for 3 seconds cubed, right? So it's the same volume, right? Should be pretty straightforward. Okay. Now, the number of nuclei that form during some time increment is just going to be n dot times dt per unit volume of alpha. Okay. So if we assume early time before any impingement, and that every nuclei that we throw in lands in alpha, meaning that the volume fraction of alpha is still much larger than the volume fraction of beta, we should make sense that the extent of the transformation, or the volume fraction of the beta, is just going to be the sum over all of those particles. Right? So we're going to integrate this equation from t equals 0 to our current time, right? And what we get is pi over 3, the nucleation rate, times the velocity cubed times t to the 4th. Okay? So, as I said before, this is only valid for very short times, right? No particles can be touching, because once they touch, we have to adjust the growth rate of the touching particles, right? They can't grow over, they can't overlap each other, right? And it also doesn't account for the fact that when we throw in our nuclei, Some of them, if we throw them into our system randomly, some of them are going to land on regions that are already transformed, right? So we need to subtract those out, and we need to subtract any overlap between our particles out, okay? So the key thing that Avrami realized and Kolmogorov realized is that that correction is actually fairly simple, right? The fraction of this transformation, if we just plug in values here, that is in the real, right? That's not double counted, is just going to be proportional to the volume fraction of the untransformed alpha, right? So we can calculate what a correction factor for this, right? And then we plug it in, and we have an equation that looks like this, right? So if you want, you can play with the equations, but the main idea is that we need to be proportional to the amount of all of this is going to be proportional to the amount of alpha that's left. And so this equation, you can see when t is very small, this approaches 1, right? So our fraction is 0, right? It's our approximation for the exponential of small x. And that when at large times, this is going to go to 0, close to 0, so we're left with a fraction of 1. Okay, so this is sort of deriving it for a particular case. This is the particular set of assumptions, and then what does everyone do with it? We generalize it so we can use it for every other situation under the sun. Okay, and what does that generic equation look like? Right here. And this is what I expect you to know, right? This is one of those key things, right? If you learn nothing else from this class, the JMAC equation. Okay, so why is this equation useful? Well, it tells us we can describe the transformation in terms of two components, two parameters. This exponent here, which is called the Avrami exponent, and this ranges from 1 to 4, and it's going to provide us insight as to the physics behind the transformation. Maybe, sometimes, in ideal situations. I say that with huge caveats, because there's in the past there's been a lot of emphasis placed on, oh, my Avrami exponent is 3, so that tells me something. Okay, what we do know is if it's close to 4, right, we had an expression here that was t to the 4th. So if the Avrami exponent is close to 4, we know we have all of our assumptions here that we talked about at the beginning are going to be followed. Random nucleation, isotropic growth, growth until impingement. Okay. We also have oh yeah. Yeah, I think it's fair to say that you'll see an exam. You'll see a question on the exam where you'll use this equation, right? more than likely, you'll see a question on the exam that relates to these bullet points that I'm going to talk down here. Okay, so n is the exponent. K here provides insight into the rate of the transformation. So if we go back and we look at what's on K, well, K includes two terms. It includes our velocity. Well, it actually includes three terms. It includes our velocity of the interface. It includes our nucleation rate, and it includes a geometric factor that accounts for the shape of the particle. Right? So there's a shape factor, nucleation rate, and growth rate are all get wrapped up into K. Right? Remember, we don't have any physical way of separating out whether our change in volume fraction is because we have a whole lot of particles or we have one particle that's just growing really fast. Right? There's no way to separate that out in this framework. Okay? So N tells us something about how the physics of the transformation. K tells us the rate. Okay? So here's why this is really useful. Right? So we've got an exponential thing here. Let's take the log of both sides. Right? And in fact, we'll do something silly and we'll take the double log, right? And we'll plot this on a log scale. Okay? What happens when you plot anything on a log scale?
I seem to remember this from, I might be completely wrong here, but doesn't it basically become flat?
Anything that almost any function, if you plot it on a log scale, becomes linear. Log scale becomes linear.
Yeah.
Right? Okay. Now we're going to do something crazy and we're going to throw in another log.
Are you sure that you're not just making this up?
I'm not making this up.
What scientist in history decides, okay, I'm going to take the log of this and the log of this. Now what happens when we take the log of this again? I mean,
because what it does, okay, if we plot this on a log t, right? If we plot log t and the log of 1 over f of f, we get an equation that we can directly determine the constants n and k from. Right? So we should have a straight line then that has a slope of n and a y-intercept of natural log of k. Right? And if this line is straight, it tells us that our mechanism is constant throughout the whole transformation. If our slope changes, if we're not straight on this curve, it means that we have fundamental change in mechanism that's occurring from the beginning of the transformation to the end of the transformation. Or we have some other systematic deviation occurring. Like I said, I recently did a computational experiment where we were looking at dynamic recrystallization. In that case, we're deforming while we're nucleating and growing new grains. So that means we have regions of our transform microstructure that can renucleate, right? Because those grains keep deforming and they build up energy, right? So we have a decreasing Avrami exponent because it would be, in this case, if some of the beta transformed back into alpha would be the equivalent, right? But that's a deviation I don't really want to get down on. Okay, so for a homework exercise, you'll be given data and you'll have to plot it and then make some kind of insight. Probably something very similar for the exam. Okay, so K was thought I messed up. These should be n's. How did I not see that before? Okay, so interpreting the exponent, that is correct. All of these k's should be n's, not k's. So the exponent was thought to have an integer value between 1 and 4, right? And it's the integer value reflects the nature of the transformation in question, right? So as we talked about before, we have a value of 4, which we have 3-dimensional growth and a constant nucleation rate. Okay, so if we have site-saturated nucleation where all the nuclei are preformed, we end up with a K value of 3. If the nucleation occurs on specific sites only, like grain boundaries or impurity that rapidly saturate, but then we can grow unhindered, right? If we have large grains and nuclei only appear at the grain boundaries and then they can grow and take up the whole grain, we get values that are on the high side, 3 to 4, right? Obviously, we're not going to have an integer here in this case. If the distribution of nucleation sites is non-random, the growth can then be restricted to 1 or 2 dimensions, right? So, for example, if we're nucleating from surfaces, edges, or point sites, we can get Avrami exponents that are 1, 2, or 3. If we are talking about transformation on a surface like epitax, like something we have an epitaxial thin film layer that's transforming, we're going to have a lower Avrami exponent. Okay, so this is why I said we can sometimes get some information on the physics. It's not like we have a lookup table and say, oh, my exponent's 3, that means this. No. It's a non-unique lookup table. There's many ways, many sets of physical ways the transformation can proceed that will give you the same Avrami exponent. It's a many-to-one type mapping, right? But if you know how the experiment was performed and you know how the phase transformation is occurring in general, then the Avrami exponent can tell you something about details you can't observe directly, right? And that originally, when people first started analyzing it, they thought it should always be an integer. However, you can show that if you limit your nucleation to not be homogeneous and you only allow heterogeneous nucleation at certain sites, then Avrami, the exponent will most definitely not be an exponent. It will be a decimal, right? Right. And so that wraps up the diffusional phase transformation. Starting Friday, we're going to talk about sintering. Monday, we're going to do grain growth. And then before the break, we're going to get started with diffusional vitrification and crystallization. And then the last topic will be Martensitic transformations. And that's going to essentially wrap up the semester for us. So, and then with any luck, we'll have a little bit of time to review some key important points and look at some case studies. All right. So Have a good Wednesday. Stay safe, stay healthy. Oh, there's missing. Yeah, let me. I thought those all the lectures I thought should have been auto posting. I'll double check. But if there's a couple that didn't make it up from last week, I'll check and do it right after this. Okay. Take care. And again, midterm replacement, contact me if you're interested.